All right. This next section, 5.2, binomial probability distributions. The beautiful thing about this is this topic here discusses how do you do statistical analysis on events that are binary. What does binary mean? Two. Yeah. So binomial means two things. These are events that yes, it can, or no, it can't happen. On, off, good, bad, right, pass, fail, those kind of stuff. These are these are analysis of how do we analyze those data. Note, very, very important. If we have pass, fail, success, fail. So would you always think that success is a good thing and fail is a bad thing? No, it's not always the case. Because what if you're analyzing, what if you're studying number of time people trip? Do they trip or do they when they're walking upstairs, do they trip or not? So the success there would be, did somebody fall? A failure would be they walked up the stairs without falling. So don't let it fool you thinking that a success is always a good thing. We talked about coin flips. It could be a head or a tail. We can determine that. Birth of a child, boy or girl. So these are binomial probability distributions, which means there are only one of two categories, two possibility of outcomes. Here are the definitions and the conditions. A binomial probability distribution results from a procedure that meets four requirements. The first one, the procedure has a fixed number of trials. When we say trials, we mean events or observations or outcomes. So, and like you can flip a coin, that's a trial. Walking upstairs, that's a trial. So they have to be finite. The trials must be independent. What does independent mean? What does independent mean? If the trials are independent, okay, if they're dependent, what does that mean? Yeah, the one event depends on the outcome of another event. So if they're independent, means their outcomes are not dependent on those of other trials. Case in point, when we deal with picking a card from a deck of cards, do you put the card back or you don't put it? So with replacement or without replacement? Because if you don't put it back, you've changed the probability of the next result. If you do put it back, then everything's the same. So there has to be a fixed number of trials. Each trial must be independent. Each trial must have all of its outcomes classified into one of exactly two categories. One of exactly two categories. So at the most you can have are two possible outcomes. Each event must fall in one of those two categories. And lastly, the probability of a success remains the same in all trials. Probability of success is the same. Like I said, the picking a card from a deck. Can you make picking a card out of a deck a binomial experiment? If so, how would you do it? Black or red? Yeah. But choose a card. Is it black or is it red? Ideally, what would you think? 50-50. But we're going to see this later on that yes, that's true if you have infinite number of events. But if you do a small finite set, it'll be one way or the other. It'll be more skewed. So in order for us to talk about this, you have to first define these four categories. If it doesn't match all those, then you can't go on further with any of these formulas. Notation for binomial probability distribution. From now on, I'm simply going to write BPD. S is for success. There are two categories. It doesn't have to be P or success failure. It can be pass fail. It can be good, bad, right, wrong, on, off. But they have to be binomial in their structure. The probability of a success we denote as little p. And for probability of failure, we'll call it little q. Remember, now since these are binomial or binary in results, the probability of success plus the probability of failure has to equal 1. So the probability of success could be found by 1 minus the probability of your failure, or the probability of your failure can be calculated as 1 minus the probability of your success. Which can be rewritten as 1 minus Q or 1 minus P. What does N always represent for us? The number of trials that you're having has to be finite. In other words, it has to be a solid number. Can't be infinity. Now, since we have an N number of events that can be done, X is the actual number of successful or successes and X has to be within that domain of your number of trials. What does this mean? If it's 0, that means you had no, is it possible to get 0 successes? Yes. Or you can have all successes. P is the probability of a success in one trial. Q is the probability of failure in one trial. Not the cumulative of all of them, it's just one event. And lastly, P of X is the probability of getting exactly X successes in the set of trials. That sets us up because now we're gonna have to start looking at some examples and we're looking at some specific formulas later on that are gonna get kind of complex. The first example. An adult smartphone owner is randomly selected with replacement. Why is that important? When an adult smartphone owner is randomly selected with replacement, why is that important? Why do I have to mention that it's with replacement? What happens to all future probabilities if I don't replace that person? How? It doesn't skew the data, it skews the results. How does it skew the results? Well, remember, these are binomial. They can either be success or failure. Are all the probabilities the same if you let one go? No. So you have to have with replacement whenever you deal with events that deal with people or items. So when there is a 0.05 probability that this person is cashless, which means they never carry cash. We want to find the probability that among 10 randomly selected individuals, adults, exactly two of them are cashless. Question one. Does this procedure result in a binomial distribution? Question two. If this procedure does result in a binomial distribution, identify the values of n, x, p, and q. So we have 10 people we're selecting and the probability, hmm, does this procedure result in a binomial distribution? Yes or no? Why? You can't just say yes or no. You have to tell me why. It's the why I'm interested in. I don't care about the yes or no. That's it. Look at your notes. We just talked about, wrote down what you spent the first 10 minutes of class or 20 minutes of class writing. What are the conditions for binomial distribution? Okay, yeah, let's go step by step. Question one. Does it have a fixed number of trials? Yes or no? How many does it have? It has 10. So yes, it's finite. What's number two? Are they independent? Yes or no? Are they independent? Why? Yeah, each person is chosen and put back in the list. So yes, with replacement. What's the third condition? Are there only two categories? Yeah, they're either cashless or not. What's the fourth one? Does the probability remain the same for each trial? By probability, I mean probability of success. So are all the probabilities the same? If yes, then what are they? Yes. Each person has a 0.05 probability of being cashless. So since number one is true, then we have to define N, X, P, and Q. What is N? N represents what? What does it represent? Number of trials, which is how many? 10. What's X represent? Which is what in this case? Exactly 2, right? So what's the probability of success? 0.05. So what's the probability of failure? 1 minus P. 1 minus 0.05, 0.95. So before you go on any further with these things, you have to make sure that that is true, that those four conditions apply, and then label a NXPQ, and then from there we'll start plugging into the formulas. Remember earlier in the semester, we talked about this. The 5% guideline for cumbersome calculations. If you look at the bottom of your page, you'll see it down there what it says. The 5% guideline for cumbersome calculations. We use this whenever we have an exceptionally large data set or a sample size, because normally we're supposed to have with replacement. But what happens, can you have an example where you don't where you have it without replacement? Can you perform a binomial probability distribution without replacement? Because if it's without replacement, what happens to the next probability? It changes. That's where the 5% guideline for cumbersome calculations come in. If your sample size is less than 5% of the overall data set that you have, then you can use without replacement in your data set. So for example, if my N was 250,000, what's 5% of my N? No. What's 10%? You're close there. It's what? Because it's 250,000. 10% is move the decimal place one over to the right. So 10% would be 25,000. 5% would be half of that. So if your sample size is less than 12,500 of these 250,000, then we can use without replacement without losing generality. Because it's so small that it really won't affect it that much. So far, so good. So you have to remember, so 5% is move the decimal place over one, whatever you have there divided by two, and you actually get your 5%. Now, the crux of this rest of this section, are we going to talk about the three methods for finding binomial probabilities. The first one, we're going to talk about dealing with formulas and do the calculations using formulas. The second method, using technology. Using a calculator or computer to do the work for you. The chart from a table. There's in the old days, they didn't have calculators and stuff like that. We used to have to carry huge books with all sorts of tables and charts in there. And that's where our numbers would come from. So the computers and technology ones, I'm not going to go over that one too heavy because that doesn't do much. How many of y'all know how to use Excel? Okay, the rest of y'all should learn how to use Excel. Calculators, again, there's I really don't use calculators because they change every other a couple of years. They change with a whole new set of calculators. So I don't deal with those. So we're going to spend most of the time talking about formulas. This is formula 5-5, binomial probability formula. Before we talk about this, I have to define something called a permutation. What is a permutation as opposed to combination? You ever hear the word permutation? Not even in science fiction? What's a mutation? A change. So per change is each change that can occur. So what that's saying is A and B the same thing as B and A? No, because they're different positions. So we're looking at the number of possible changes that can occur with your data sets. The formula we're going to be defining actually it really should be P here. But for some reason, the textbook wanted to use C, which is a combination formula. This symbol here is called a factorial. Put your phone up. You don't need it. What it means is you take everything from n all the way down to 1 and you multiply them together. So 3 factorial would be 3 times 2 times 1, which is 6. These are methods we use for counting. What this thing does is tells us the number of changes that can occur. Now, let's go ahead and work a couple examples of this first to see how it's simplified. You don't need a calculator for this. So let's say our n was 6 and our specific x value was 2. What this is saying is how many different changes can you have if you have 6 objects and you put them in groups of 2? That's what it's telling you. So what you're looking at here is where the first number is the n, so you have 6 factorial, 6 minus 2 factorial times 2 factorial. It is for combinations, but it's the number of changes we're looking at. So the formula there is for a C, but they're defining permutations. If you read that also, what you have there, instead of just looking at the symbols, it'll tell you that the number of permutations is that. So again, just don't look at the formulas. You have to read everything else behind it. So now let's look at this. Let's keep on going. What this thing says, we have 6 factorial. 6 minus 2 is 4 factorial. The general rule with permutations and combinations is every number in the bottom has to be eliminated. Because what this does, this is a counting technique, you have to have an integer. Actually, it has to be a whole number. So on top, we have 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And 2 factorial is 2 times 1. We see that 4 down to 1 cancels. The 2 goes into 6 3 times. So it equals, there are 15 different ways I can combine these, or possible changes I can have. Everything in the bottom has to disappear. Because if you don't, then you have a decimal, as I have a rational number. So that's how you find the counting, the number of possible ways of doing something. All right, so let's build the rest of the equation. So the probability of an event occurring, a binomial probability event, is NCX PX. So what does P represent? Probability of what? Of success. We're dealing with success or failure. So P is the probability of success, and we're looking for X number of times. So if that's success, then the number of failures is N minus X. So Q is the probability of a failure, P is the probability of success, and to those exponents. So remember the first example we had. It asked us to find N, X, P, and Q. Because that's what you have to define to use this formula. You have to define all 4 of these variables. So in our first example, what do we have? What was our N? 10. Our X was 2. Our probability was 0.05. And probability of failure is 0.95. So we're looking for exactly 2. We're looking for exactly 2. So x is 2. So we have 10 minus 2 factorial times 2 factorial. P is 0.05 to the power 2, 0.95 to the power 10 minus 2. It's just plug and play. We find these and plug them into where they belong in there. So 5 to the power 8. So we have 10 times 9 times 8 factorial. Ten minus 2 is 8. So from 8 down to 1 cancels. And 2 is just 2 times 1. So that cancels the. So we got 45 possibilities. What that gave us is 0.074635. And of course, you can have more. Again, when you get this far, it's easy to use your calculator because in your calculator, you have a button that looks like this. You press that, the first number you enter is this bottom number. And the next number you enter is the exponent. And it does all that work for you. Now, this number can get pretty large. I mean, it has many decimal places. Rounding rule, which we call significant digits. We only want 3 significant digits in our final answer. Only in the final answer. Don't round anywhere before the final answer. Because if you do round these numbers halfway through, or if you found these numbers and you round those to 3 decimal, that's called a rounding error. And it's going to give you a very, very wrong error at the rounding number at the end. So the only time you ever round your final is your final answer. Let's see. Oh, overtime football. The next example. I'll put this one down so we can take a look at it. This one here. We noted that between 1974 and 2011, there were 460 football games decided in overtime. And 252 of them were won by the team that won the overtime coin toss. Do y'all know how that works, how overtime works in football, or the old days, how it used to work? If the score was the same score, tied score, then they would flip a coin. Whoever won the flip of the coin would get the ball first. Whoever made the first point after overtime would win the game. So you see why the person who wins the coin toss would usually win the game, because all they have to do is make a field goal and they'll win. And they changed that recently, said you have to, whoever makes, they both have a chance with the ball. Whoever makes the high score after one possession, then that person wins. That still didn't help. So let's look what happens here. Is the result 252 wins of the 460 games equivalent to random chance, or is 252 wins significantly high? Well, remember what do we call significantly high? How do we define significantly high? Anybody remember? What defined as significantly high or significantly low? 2x? Or was it? You're right. What's that? If it's if any number is higher than this one, which is the mean plus 2 standard deviations. This is with samples, this is with populations. Or if it's greater than this, it's significantly high. If it's less than this, then it's significantly low. Remember, since we're dealing with a binomial distribution, we have to label these 4 variables. However, and since we're looking for a general number, we can't specify the number of x's yet. So in our example, what is our n? 460, because that's how many games we had. What is our p? What's the chance of winning a game? 50-50. No. You know, it's the other number, no, not just yet. Because what we're looking here is 50%. So 0 0.5, 0 0.5. The chance of winning or losing the game is the same. Because why is it the same? Because remember what they said. Is the chance the person winning the coin toss going to win the game? So what's your chance of winning the coin toss? 50-50. Now, so what's this before? So this one is the result of 256 wins easy in a random chance, or is it significantly high? Can we answer the question by finding the probability of 252 wins or more? Because that's what our X is going to be. Our X is going to be 252 or more. So are we going to do that? No. But we have to go from 252 all the way to 460. We'd have to find the probability of each one of those and then add them all together. So how would you solve this? Computers. There's no other way to do this other than computers because we have to first do 252. Then we have to do 253, then 254, and so on and so forth, all the way to 460. Too much time. So we set the computer off to do it. For example, like this. We set your number n as 460, the probability of success, and now we're going to look at it does the probabilities for us. All we have to do now is just copy and paste those, add them all together, and that'll tell you the probability. So be very, very careful about what it's asking, how we define it. Mean and standard deviation. For critical thinking. Binomial distributions, we first discussed what we call discrete probabilities. Probability distributions. Where we're looking at exact values for discrete probabilities. And binomial probability distribution is a subset of those. Now, the reason they're called discrete is because the possibilities of an outcomes are exact. It's either, in this case, it's either going to be one or the other. Which means for our mean, we're going to do the mean, the variance, and deviation. These are standard. Do we use alphabet letters or do we use Greek letters to define these? We're going to be using Greek letters because what they're looking for, remember, Greek letters are to define populations. And that's what we're looking at. Since we know the population probabilities, we have to use the Greek letters. So the mean is the mu. It's determined by the number n, the number of events you have, times the probability of success. The variance is rho squared. And that's the number of events you have, the probability of success times the probability of failure. And the deviation is simply the square root of that. So remember when we talked about significantly high versus significantly low. The mu plus 2 rho, the mu minus 2 rho. So if we look at these as formulas, it's n times p plus 2 times the square root of npq. np minus 2 times the square root of npq. Is x ever involved in there anywhere? No, we're just looking at general population values. So let's look at the football one. For our football one, we defined what NP and Q were. Using parameters to determine significance. So we had N was 460 overall games. X we didn't need. We had P was 0.5, which is 50%, and the probability of failure is the same. They're called parameters because they're looking at they're summarizing, they're analyzing the population with respect to a sample size. So the mean is n times p, which is 460 times 0.5. 0.5 is a half, so half of 460 is 230. That's my mean. Standard deviation is the square root of NPQ. So we have 460 times 0.5 times 0.5 and square root that. So the half of 460 is 230. Half of 230 is 115. And the square root of that is just a little bit over 10. In this case, it's 10.7. Rounded one decimal. So what do these numbers represent? What's the units of these numbers? What was N? 460 what? Games. So mu is 230 games, and the rho is 10.7 games. We're looking at number of games. Now, for the significance, for high, we need mu plus 2 rho. For low, we need mu minus 2 rho. So we got 230 plus 2 times 10.7. 230 minus 2 times 10.7. Ten point seven times 2 is 21.4. Plus 230 is 251.4. So anything larger than 251.4 is significantly high. For any x larger than 251.4 is significantly high. Two 30 minus 21.4. 21, so 230 would make it 8.6. So any numbers less than 208.6 means it's significantly low. Let's see. Actually, that's about it for that section. The rationale behind it. So let's move on to the next section, the last section of this chapter. Or do we have time?